Welcome everyone to this session. I'm Liz Stuart. I serve on the board of the Society for Research on Educational Effectiveness and also organized this SREE conference session that we hoped to do in March, but we'll now do via Zoom right now. It's going to be in a condensed format though, so it's going to be a whirlwind tour of mediation analysis, both sort of the fundamentals and also some new and exciting sort of movements sort of in the new and important advances in mediation. So again, I don't want to take a lot of time here, so I am going to turn it right over to the speakers. We have 3 speakers and then a discussion from Guanglei Hong. Our first speaker, who I will turn it right over to, is Trang Nguyen, who works with me at Johns Hopkins Bloomberg School of Public Health. And her slides are here, and so I will let her take it away. Thank you.
Hi, thank you, Liz. So the paper I'm presenting today is actually forthcoming in Psych Methods, and it is about the first step in mediation analysis effect definition. Okay, so mediation analysis has been with us a long time. The original desire is to understand the mechanisms of the effect of an exposure A on an outcome Y. Often the interest is in a part of this effect that is through an intermediate variable M, which we call a mediator, and this effect is called an indirect effect. The idea is that the total causal effect is the combination of direct and indirect effect components. Traditionally, effect definitions in mediation analysis were model-centric. We probably all know the definition of the indirect effect is the product of 2 regression coefficients. In the last 2 decades, the causal inference approach has been applied to mediation analysis, and this resulted in a revision of effects and freeing them from the models. The result is what we call natural direct and indirect effects, which decompose the total effect. In addition, causal inference also brings in the idea of sequential intervention, which leads to another effect type, which we call interventional effects. These do not decompose the total effects, but they fit a different desire, the desire to learn about effects of hypothetical conditions, which is relevant to both intervention research and disparity research. Given that many effect definitions exist, our proposal for researchers is simple. It is simply to choose the target effect, also called estimand, based on what we want to learn. And in the paper, we talk about this using the simple setting of a point-in-time exposure followed by a mediator measurement followed by an outcome measurement. So talking about estimands, ideally the estimand should be carefully selected, and then it drives the analysis, including judgment of identification and choice of statistical methods for estimation or hypothesis testing. The question is, of the many effects and effect types, which one best matches my research question? So as a first level match, if the research question is about explaining the causal effect of the exposure on the outcome, for example, if we find ourselves asking questions like, what are the mechanisms of this effect? What part of this effect is due to the exposure's influence on this intermediate variable and what part is not? Or is the effect partly due to the exposure's influence on this intermediate variable? Then the closest estimands that match these questions are the natural direct and indirect effects. These are effects that decompose the total effect, and a natural indirect effect can be interpreted as an effect on the outcome of the exposure's effect on the mediator. We note though that these decompositions are not unique. So to define these effects properly, we need some notation. Here we have the observed variables A, M, Y. We also have potential variables So M1 is the potential mediator value if exposure was set to 1. Y0 is the potential outcome if exposure was set to 0, etc. And for mediation analysis, we also use Y of little a, little m, the potential outcome when exposure was set to little a and mediator was set to little m, and also the nested potential outcome Y of a m a prime, where exposure was set to condition A and mediator was set to the potential mediator value under condition A prime. We invoke a bunch of consistency assumptions which connect potential variables to observed variables and also connect among different types of potential variables. So the natural direct and indirect effects are defined at the individual level, and they decompose the individual total effect. The total effect is the difference between Y1 and Y0, we all know that, which we can rewrite as the difference between these two nested potential outcomes. There are two decompositions of the total effect in this setting. Each of them uses a third potential outcome, either Y of 1M0 or Y of 0M1, to split the total effect contrast into two contrasts, a natural direct effect and a natural indirect effect. And we can see here that the natural indirect effect, that each natural indirect effect, the 0 or the 1, is the effect of the outcome, is the effect on the outcome of the exposure's effect on the mediator due to the shift of the mediator value from M0 to M1. Generally, we target average effects, which are the averages of those individual effects. And there is a question here about which of these decompositions to use, and we refer you to our paper where we discuss this question. We also want to note that the natural direct and indirect effects are not identified if there are intermediate confounders, that is, confounders of the mediator outcome relationship that are influenced by the exposure. This is not a problem for effects of the next type. So let's now switch to that other effect type. If the research question is not about decomposing the total effect, but it is a what if question. So for example, in intervention development effect, we may conduct a trial to test an intervention program. And then in addition to the effect of the program as it is, we may be interested in questions such as, what if the program is modified, removing elements that affect a mediator, or retaining only elements that affect a mediator, or modified in some other ways? In disparity research, we may ask what would happen if we could shift the distribution of a factor that contributes to disparity. If so, then we want to consider the class of interventional effects. This is a large class of effects, which includes a lot of the well-known and also less well-known effects in the literature, but not the natural direct and indirect effects. An effect in this class is a contrast between a possibly hypothetical active intervention condition and a comparison condition. And an intervention condition here is a condition that sets the exposure and or the mediator each to a specific value or to a distribution that is either known or is identified based on data observed in the current study. And this intervention doesn't change anything else. To select an intervention effect, we simply need to answer two questions. Which condition best matches the what-if condition of scientific interest? And what is the most appropriate comparison condition? Let me just give some examples. So here we have a traffic safety intervention that is effective partly because it increases bicycle helmet use. Say there is now a new law requiring helmet use, and we're interested in knowing the effect of the intervention in the new context. If we assume that compliance to the law is 100%, then the effect of the intervention in the new context is a controlled direct effect, which is the difference between y of 1 little m and y of 0 little m, where little m is 100. If we assume that compliance is not 100%, but is a certain distribution, which we call squiggly m for randomness, then the effect we're interested in is a generalized direct effect, contrasting conditions where the mediator is quote unquote set to this distribution. In this example, we have a safer sex intervention for youth, and a mediator is self-efficacy, say self-efficacy for user protection or for safer sex negotiation with a partner. For some reason, say budget cuts, we need to trim the intervention down. So we may ask, what if the intervention is modified to remove elements that target self-efficacy? Then the effect of the modified intervention is represented by this contrast where the comparison stays the same. But the active intervention here sets the exposure to 1, but sets the mediator to the distribution of self-efficacy under no intervention. This here is the same example, but we're looking at another mediator, access to protection. The question is, what if we modify the intervention to zoom in on access to protection and trim out all other elements? Then this contrast represents the effect of the modified intervention. In this other example, we have 2 mediators, depression screening and depression therapy. And the alternative intervention we're considering targets therapy, but not screening for depression. It would not be complete if we do not mention the interventional direct and indirect effects. The emphasis here is on direct and indirect. These are well-known effects, but they are arguably not as relevant as some of the effects mentioned earlier if we think about specific research questions. Note that in the special case where there are no intermediate confounders, these are equal to the natural direct and indirect effects. And I have one last example to show the flexibility of the class of interventional effects. The question here is, what would be the effect on Black folks' survival in America if we could lower the frequency of traffic stops they experience down to halfway between the actual level and the level experienced by non-Black folks, everything else being equal? Here, the mediator distribution, the interventional distribution is a half-half mixture of the traffic stops distributions of the 2 groups. In the paper, we have a similar example that references a school-based intervention that may be of interest to SREE members. So to sum up, there is a wide range of effect definitions of these 2 types, and this provides researchers with ample flexibility in defining effects that match the research questions. Thank you.
Okay, so without further ado, we're gonna roll right along. And our next speaker, so Xu can get her slides up. Our next speaker is Quynh from the University of Pittsburgh.
Hi everyone, I'm Quynh. Today I'm going to present a simulation-based sensitivity analysis strategy for causal mediation analysis. This is a joint work with Yang. Our study is motivated by the job search intervention study, which examined the impact of a job training intervention on unemployed job seekers through a randomized experiment. The intervention program consisted of 5 4-hour training sessions aiming at enhancing unemployed job seekers' capability and motivation for obtaining new jobs and improving their mental health. The study randomly assigned a sample of almost 2,000 unemployed workers. The treatment group has almost 700 individuals, and the control group has over 1,000 individuals who received a booklet very briefly introducing job search methods. Our desire is to understand the maximum through which the intervention operates. In our hypothesized mechanisms, the job search intervention program enhances one's job search self-efficacy, which further decreases his depression level. In other words, participants' job search self-efficacy mediates the effect of the job training intervention on their depression level. The direct arrow from the treatment to the outcome captures all the other possible pathways that transmit the intervention impact. We aim to decompose the total treatment effect into a natural indirect effect transmitted through the hypothesized mediator and a natural direct effect representing the contribution of other unspecified pathways. As Trang clearly introduced, each effect is defined as a contrast of two potential outcomes for each individual. However, only the potential outcome under the individual's actual treatment condition is observable. To identify the average direct and indirect effects, we need to relate the unobservable quantities to observed data. The identification is complicated by the existence of confounders. As shown in this diagram, there may be variables that affect both the treatment and the mediator, or affect both the treatment and the outcome. There may also be variables that affect both the mediator and the outcome. We call these variables confounders. The confounders of the mediator-outcome relationship may either precede treatment or be affected by treatment. Here, we assume that all the confounders precede treatment and name them as pre-treatment confounders. In the job search intervention study, observed pre-treatment confounders collected 2 weeks before the intervention include participants' level of depression and demographic variables. The identification of the natural indirect and direct effects relies on the sequential ignorability assumption, which states that within levels of the observed pre-treatment confounders, the treatment is as if randomized and the mediator is as if randomized in either treatment group. Under the identification assumptions, different strategies have been proposed to identify the effects. A regression-based approach involves a mediator model and an outcome model, which adjust for the pre-treatment confounders and take into account a possible interaction between the treatment and mediator. A simulation-based approach generates the distribution of the unobservable Y1M0 as Trang defined via Monte Carlo simulations. A weighting-based approach uses a weight to transform the distribution of the mediator in the treated group to resemble that in the control group within levels of pre-treatment confounders. Such transformation enables us to relate the unobservable Y1M0 to the observed outcome in the treated group. The strong ignorability of the treatment is guaranteed by random treatment assignment. However, the strong ignorability of the mediator may not hold, even in a randomized experiment, because the mediator is generated in a natural process. It would be violated if there was an unmeasured confounder of the mediator outcome relationship. A sensitivity analysis is therefore necessary for determining whether potential violations of the assumptions would easily alter causal conclusions. Different sensitivity analysis strategies have been developed for causal mediation analysis in the presence of unmeasured pre-treatment confounding. Each method has at least 2 of the following 3 limitations. It either relies on correct specifications of the mediator and outcome models, fails to consider the influence of unmeasured confounding on the standard errors of the cause effect estimates, or lacks intuitive interpretations of the sensitivity parameters. To overcome these limitations, we developed a simulation-based sensitivity analysis strategy. As shown in this diagram, we assume that a pre-treatment covariate U is the only omitted confounder. The goal of this study is to understand what the indirect and direct effect estimates and their standard errors would have been had we adjusted for U. To reach this goal, we derive a conditional distribution of U based on our assumptions about its prior distribution and its relationship with the outcome and the mediator. And given random draws of U from its conditional distribution, we are then able to estimate the effects after the adjustment for U. For illustration purposes, we consider a simple setup in which both the treatment and mediator are binary, the outcome is continuous, and U is independent of the observed confounders. The complete data likelihood can be expressed as the equation shows. For mathematical convenience, we focus on a binary U so that we can factorize the conditional distribution of U as shown in this equation. by fitting a regression of the outcome on the mediator, treatment, observed pre-treatment confounders in U, and by fitting a regression of mediator on the treatment, observed pre-treatment confounders in U, we could use the coefficients of U in the two models as sensitivity parameters to intuitively represent the confounding role of U. We have an additional sensitivity parameter, which is the probability of U equals 1. This determines the prior distribution of U. Based on this, we could easily obtain the conditional distribution of U. The challenge is that except for the given sensitivity parameters, the other model parameters are unknown. And the estimation of these parameters is actually dependent on U. Well, U needs to be drawn from the conditional distribution determined by these parameters. To solve this problem, we adopt a stochastic EM algorithm. The basic idea is that we give initial values of these unknown model parameters and simulate U, based on which we could update these model parameters. We then iterate this procedure until convergence. We could then assess sensitivity based on the following algorithm. In step 1, to evaluate the influence of U of different strength, we specify a range for each sensitivity parameter and divide them into a grade. In step 2, for each cell of the grade, we generate U based on its conditional distribution. In step 3, given the sensitivity parameters and the simulated U, we estimate the adjusted natural indirect and direct effects and their standard errors based on a chosen causal mediation analysis method. The estimate obtained from this step is based on one random draw. Therefore, to obtain more accurate estimates, in step 4, we repeat step 2 and step 3 n times for each pair of sensitivity parameters. In step 5, we combine the adjusted estimates over m replications using Rubin's rule. In the application, we use the weighting-based causal mediation analysis method to estimate the natural indirect and direct effects. For illustration purpose, we focus on the indirect effect here. We found that job search self-efficacy significantly mediated the intervention impact on depression level. The indirect effect is estimated to be -0.03. We then conduct a sensitivity analysis and visually represent the results. The axis here, the x-axis here is the coefficient of U in the logistic regression of the binary mediator, and the y-axis is the coefficient of U in the outcome model. While pi, the marginal probability of U equals 1, is fixed at 0.5. Each black curve represents the combinations of sensitivity parameters that lead to the same indirect effect estimate as indicated by the number on the contour. The sensitivity parameters along the red dashed curve reduce the estimate to 0. In the region between the two blue dotted curves that bracket the red curves, the effect is changed to be insignificant at the significance level 0.05. Each black curve, as you may find, tends to be parallel to an adjacent black curve, but not to an adjacent blue curve. This actually indicates the change in the standard error after the adjustment for U. Each dot corresponds to the conditional associations of each observed confounder with the mediator in the outcome, which are used to calibrate the strength of the sensitivity parameters. This sensitivity plot indicates that for the original causal conclusions about the indirect effects to be changed, U has to be much stronger than the most important observed pre-treatment confounder. Given that this is highly unlikely, the results are robust to the unmeasured pre-treatment confounder when pi is at 0.5.
Two minutes left.
Thank you. And to further evaluate the influence of the prior distribution of U, we draw two additional sensitivity plots when pi equals 0.1 and 0.9 respectively. Clearly, it becomes even harder to change the original conclusions when pi is further away from 0.5. An important note is that whether the proposed sensitivity analysis method can recover the true effects depends on the robustness of the chosen causal mediation analysis method to possible model mystifications and the specification of the observed part and the unobserved part of the models, which determines the conditional distribution of the unmeasured confounder. Through simulations, we found that it is crucial to correctly specify the unmeasured confounder's relationship with the outcome and the mediator, no matter which mediation analysis method we adopt. Given that such relationships is unobserved, it is purely determined by theoretical reasoning. If a potential interaction between you and the treatment or the mediator exists theoretically, we need to modify the conditional distribution of U accordingly and adjust for these interactions in the adjusted causal mediation analysis. And the influence of the mystification of the observed part of the mediator or outcome model is relatively small. In particular, the sensitivity analysis strategy is robust to mystification of the observed part of the outcome model when implemented in the weighting-based method. In addition, a mystification of the mediator model usually generates a smaller impact than that of the outcome model. In summary, the proposed method has 4 major advantages. First, it enables education researchers to intuitively evaluate sensitivity parameters in reference to prior knowledge. Second, it accurately reflects the influence of unmeasured pre-treatment confounding on the estimation efficiency. Third, it provides a convenient tool for visually representing the sensitivity analysis results. And lastly, it can be implemented in different causal mediation analysis methods. And here are the references that I mentioned in the talk. Thank you.
Great, perfect timing. Thank you so much. Wonderful. So we are now, oh good, I see some people using the little hand clap thing in Zoom. Great, so we are on to our third presentation from Brian Vegetabile of RAND, the RAND Corporation, with co-authors listed here. So Brian, I'll turn it over to you. Thank you.
Thanks. I'm Brian Vegetabile. I'm an associate statistician at the RAND Corporation. The title of our talk is Identifying Potential Mediating Variables Using Variable Importance Measures. And so we're going to take a non-parametric spin on causal mediation analysis. And this is joint work with Donna Kaufman at Temple University, Megan Schuler, who's one of my colleagues at RAND, and Daniel McCaffrey at Educational Testing Service. Just to acknowledge, this is work funded by NIDA and NIH. The opinions are solely mine, and we can get that out of the way and move on. You know, you've sat through 2 talks, you get the idea right now that a goal in a lot of studies is to identify the mechanism by which a treatment or intervention really affects an outcome. So if you have some exposure, there's something that's occurring in between the exposure and the outcome. And it recognizes this fact that unless the outcome is measured immediately after the application of the exposure, many things could have happened. So the exposure could have impacted some other variable that itself is the reason for the effect that was observed. And so in this talk, we'll talk through non-parametrically modeling relationships among variables and using variable importance measures to hopefully identify potential mediating variables that can help facilitate explanation. To set up in my talk, this is the notation and some ideal structural assumptions. So A is going to be an exposure throughout this, Y is our outcome of interest, M is the mediator, and X is the covariate information. Ideally, the exposure A would have been assigned completely at random. That's the dotted line in the figure, as in a randomized control trial, but there may be paths from the covariates through the mediator and to the outcome. The mediating variables are quote unquote on the path between the exposure and the outcome. So A affects M, which affects Y. And the directed acyclic graph implies a temporal ordering. Specifically, covariate information is measured before exposure. The mediator occurs after the exposure and before the outcome, and these temporal assumptions are important. The historic approach to this is through Barron and Kenny, which uses a series of linear regressions to decompose the overall effect into its pathwise components. So it takes these series of regressions, it takes model 2B, plugs it into 2A, and then equates the effect of the treatment between the resulting model and model 1. And so you can see here, this blue beta 1 can be equated to this new parameter delta 1 plus delta 2 gamma 1. And we can get the decomposition of a total effect is equal to a direct effect and an indirect effect that we expect that we've talked about a lot today. And the term gamma 1 delta 2 captures the effect of A through M. So this pathwise effect from A through M and into Y. In these models, as was alluded to in the last talk, there's a lot of assumptions for causality. We're talking about linearity, correct model assumptions, and it's difficult to extend the concepts of effect decomposition when there's nonlinearities or interactions among the models. But we largely want to talk through this idea of, decomposing pathwise effects, but reducing some of these linearity assumptions. So Trang did a nice setup, and so I can walk through these slides pretty quickly, but the idea is that causal mediation starts with individualistic effects using the potential outcomes framework of Nabin and Rubin that's been extended to mediation analyses. So we'll consider this simplified graph. Under this graph, we can define potential outcomes. And so similar to Trang's notation, by intervening on M and A, we get a potential outcome yi A of M. If we only intervene on the variable A, we can have a potential outcome of a mediator, which itself is introduced into the potential outcome of the overall outcome. So yi A of M of A. So this is our notation, and Trang gave a nice introduction to this, so I won't spend too much time here. But as she alluded to earlier, this is the same effect you'd get in the standard potential outcome framework. And then you have these counterfactual outcomes that arise under counterfactual mediators. So assuming that the mediator itself was assigned under some alternative process where if we set the value of the treatment equal to little a, somehow mi is set to a prime, and you can think of that as being some counterfactual process that's setting the mediator. And again, you can connect all of these together by connecting the potential outcomes due to M to the direct outcomes under the interventions. And we're now at a place where we can define effects. And as Trang alluded to earlier, this is the natural indirect effect and the natural direct effect. But this will be the setting that we're talking about today, where we started at Barron and Kenny, where you had linearity, you equate a setup of a series of models, and then you can decompose that into a direct and indirect effect. Under this setting, we have a set of just general descriptions of potential outcomes that we can decompose into direct and indirect effects. And our goal will be to model these relationships non-parametrically to get at something that looks similar to Barron and Kenny, but in a non-parametric setting. I'll talk really quickly that we have a fundamentally worse problem for mediation. So it's the fundamental problem of causal inference, is that we only get to observe one of these outcomes. We have a lot more treatments and a lot more mediators. So I like to call it a fundamentally worse problem. And so we changed the focus from individuals to expectations and populations. So we'll want to integrate over individuals within a population. So by changing this focus, you can look at these expectations of potential outcomes for an individual and then integrate over the path of the mediator. And so you can condition on the potential mediator and do a weighted average of these to get to the expectation of this potential outcome within an individual, and then redefine individual treatment effects as being functions of these expectations. And you can do this both for the potential outcomes that we can observe and the counterfactual potential outcomes. And our main results that we've been working on here are by looking at these effects, what can we say about relationships among variables? And so we can start to say, well, if there's no direct effect, what happens in these individual expectations integrating over that path? And you basically find that if there's no direct effect, the probability of the mediator value being some value M, given that A was equal to A prime, is equal to the probability of the mediator is equal to A, is equal to M if it was set to A. And this is for all M. So basically this is saying that the mediator processes are the same no matter what's going on. So there's no path there. And then you have this expectation of this potential outcome is equal to a constant for all M. And so that helps us there. And so we basically, sorry, let me step back for a second. We see that the expectation of this potential outcome at A is equal to A prime is equal to a constant for all M. So this is a somewhat nuanced interpretation that I won't talk through to here, but it shows that no indirect effect only goes through one level, A is equal to A prime. When there's no direct effect, we can do the same thing. And basically what it says is that the expectation of the potential outcome when A is set to A prime is equal to the expectation of the potential outcome was A is equal to A for all M. And so there's basically no variability in the expected potential outcomes due to the A variable. And so this is the same as saying that there's no direct path from A into Y. So as we start to look to those implications, we can turn the question back and say, what happens as different arrows are, added or removed to that graph? And so when we look at these, we can say, what happens in the observed data, specifically estimating the expectation of the outcome given A, X, and M, and the expectation of the mediator given A and X, and how does that change the graph under different assumptions? And we'll do that using variable importance measures that will allow us to assess the importance of each variable in the relationship of interest. And the idea here is that you train a full model and you get some loss. So the full model is the directed acyclic graph to the left. And then you train a nested model. And to do that, we permute one variable in the whole setup. So the exposure A is permuted, and then we retrain. And then we compare the losses under the full model and this nested model. And we find that if A is unimportant in the model predicting the outcome, then the losses will be equivalent under these two assumptions. Otherwise, the loss will increase if A is important in these relationships. And we can do this for both the mediator and the treatment level, and permute different variables to explore the relationship among these three key variables. So our analysis strategy becomes, first assessing, is there an effect of A on Y? If we understand the total observed effect, this isn't necessarily a prerequisite for exploring direct or indirect effects, but it's sort of something I think should be done first. And then you assess, is A important in predicting Y for given values of M? If it's not, the effect is mostly indirect. If you look at the exposure subset, that nuanced assumption I said before, A is equal to A prime, we assess if M is important for predicting Y. If not, then any effect is mostly direct. And then assess if the treatment is important in predicting the mediator. If it's not, the effect is mostly direct or not through M. And so otherwise there's a partial indirect through M. And basically what we did is we came up with a set of criteria to look at that is similar in spirit to Barron and Kenny by addressing paths, but now you can use non-parametric modeling. So in the paper we're hoping to get out in the next couple of months, we have a nice little simulation that explores this a bit. I won't go into this in too much detail in the interest of time. We explore whether or not, if there's an all indirect effect, or if there's some indirect effect, or if everything's direct, what happens? And the idea is that by evaluating the losses under different permutations, so in this table, the tildes imply the variable that's been permuted. So A tilde, M tilde is both of them being permuted. When everything's direct, we see indirect, we see that the loss is equivalent under these two sets of assumptions. So under permutation, the loss is about the same as under the full model. And so we can see that most of the effect is indirect. And so we suffer no loss in predicting Y. We can do the same thing if there's some indirect effect. Both of the variables are important, but M is important in the A is equal to 1 subset, suggesting that the effect is observed, is direct. And then we can also do the same thing with all direct effect. And here we see that the loss is the same on the A to M path, indicating that there's no, A is not important in predicting Y. And so we basically set out to demonstrate, can you identify potential mediators using definitions from the causal mediation framework and non-parametric estimators. And so right at the outset, we didn't talk through it, but this was all done under standard assumptions for causal mediation analysis, sequential ignorability, and the like. But in the presence of non-ignorability, the results here are associational, not causal. You've identified something that is potentially on the path, and you have a similar result to what you'd have in Barron and Kenny, but you get to use more model flexibility. And we're going to explore this in future work. But basically, you're more likely to be in the graph on the right in an observational setting than the graphs we set out at the beginning. But again, I'd contend it's important to demonstrate how non-parametrics can identify variables on the causal path in this way. Thank you.
Great. Thank you so much. And sorry, I totally butchered your last name.
Oh, no, it's fine.
Now I know.
To mention it. My advisor butchered it at my advancement, so it's not the first and won't be the last.
Oh, okay. Well, all right, I'll do better next time. Wonderful. So we will now turn it over to Guanglei Hong, who had internet challenges in the middle, but she is back with us, and hopefully she will stay connected so I don't have to make sense of her slides without her. So Guanglei is joining us from the University of Chicago, and go ahead and you can sort of try to connect the pieces and move us all along. Thank you.
So you can see my screen now?
Yes.
Good. Okay, if anything happens, Liz can take over. I sent you guys my discussion slides, so you can just address the questions I have in the slides. So, so thanks so much for the opportunity to study this set of papers, and I think all three are really interesting and eye-opening to me. And I think each of them makes a unique contribution to the literature on causal mediation analysis. And congratulations to those of you whose paper are actually coming out very soon, or at least in the pipeline. So I discussed these papers in the following order, largely because I think by Trang and Schmid and Stuart might stimulate a lengthy discussion at the end, if we have time. But just to recap, Brian's paper presented a study on using permutation strategy with non-parametric modeling to uncover important mediators in particular. And Trang and Nguyen study proposed a simulation-based approach to sensitivity analysis for causal mediation studies. And finally, the paper by Trang and others carefully explained to applied researchers a large array of causal effects related to mediation. So I started with Brian's presentation, focusing on identifying potential mediators. I found their permutation approach impressively creative. My main question for you is conceptual. I wonder if there's a connection between your permutation strategy and the randomization inference strategy. So so far as I know, in a randomization test, after the data have already been collected, so the analyst would randomize, in other words, permute the treatment indicator to all the individuals in the sample. And then he would repeat this procedure, say 500 times, and then there will be 500 estimates of the treatment effect. And it constitutes a null distribution, right? Because the treatment indicator was randomized. So, this constitutes distribution we call the null distribution. It's suitable for testing Fisher's null hypothesis, saying the treatment effect is 0 for everybody. So I understand that the key difference here is that in the current study, you do not intend to draw any statistical inference, but from your permutation tests. However, I just wonder, wouldn't each random permutation of your treatment or a particular mediator generate a random value of the empirical loss, and then you have a distribution of the empirical loss. And then perhaps you can use that for testing the null hypothesis about NIE or NDE. So it's a thought. Wonder if this is the next step you might want to take. And then I have some relatively minor comments. The first one, on your slide 16, you talk about two conditions for no indirect effect. Condition 1 is very clear, right? If A does not change the distribution of M, as A has no impact on M, then there's no indirect effect because M doesn't qualify as a mediator. Condition 2, which you didn't want to get into depth, I just wonder if it could be changed to just saying A does not change the MY relationship. I'm not sure if that's exactly what you are testing, but or you're trying to investigate. But I think that constitutes the second condition under which there would be no indirect effect. So on slide 20, maybe in relation to this, your step 4 was to see whether A would affect M, right? I wonder if it can be placed right before step 3, because if M is not mediated, then step 3 doesn't seem to be necessary. It's something minor. Lastly, I think your outcome model can be more realistic by allowing X1 and X2, those covariates, to interact with A and M, and I think that would be useful to showcase the flexibility of the non-parametric procedure. So moving on to the second paper by Xuqin and Fan Yang, it's very interesting. You know, there are some researchers in the past who have done simulations, done sensitivity analysis through simulating an unmeasured confounder U, typically in evaluating the average treatment effect. So I think this study is very original in extending this strategy to causal mediation studies. The extension is not trivial because causal mediation analysis is considerably more complex. So one suggestion I have, really quick one, is in the paper, in your table 1, you clarified which existing sensitive analysis methods has, you know, which of the limitations. You check mark, you know, each of them, these are the limitations they have. I wonder if you could add a column to show which of those limitations your strategy aims to overcome, because I was just wondering, the reader would want to know whether you actually want to overcome all of those limitations or just some of them.
Yes,
So,
actually all of them.
oh, good. Yeah, so I think it's good to clarify, you know, it will impress people to see everything got checked off. And a comment on your data generation, your slide 12, you showed your true mediator model. I think it implies a pretty strong assumption because you wouldn't allow the in your model, you didn't allow the selection of mediator to differ between the treatment group and the control group. Because of the true model, you want to be as general as possible. So I wonder if you relax that assumption, you know, how many sensitivity parameters would you end up having? And is your sensitivity analysis strategy still feasible? That's one of my questions. Slide 18. I wonder why don't you want to consider possible U by M and U by T by M interactions in your true outcome model? Again, the goal is to make your true model as general as possible. So my main comment is on the purpose of your simulations. So on slide 17, you seem to indicate that, you know, you seem to suggest that sensitive analysis method could recover the true causal effect. And I think that could be misleading to your readers because a sensitive analysis does not reveal the final truth about what the true causal effects are equal to. Otherwise, every researcher could claim at the end of their sensitive analysis, you know, we know exactly what the truths are. So I think it's only useful for assessing the amount of bias associated with a possible omission, right? So I think the purposes of your simulation study, I would suggest two. The first one is for the point estimate of each causal effect, you want to determine whether the new strategy, your new strategy produces an estimate of bias close enough to the true value of the bias associated with the omission view, right? And the second, given your interest in the sensitivity of the standard error estimate to the omission of potential confounders, I think you want to use your simulation study to determine whether the new strategy accurately captures the influence of omission of U on estimation efficiency. Those are the two goals. I'm not sure if you address the second, and I think you should also highlight the first more clearly. And then another comment, in one of your scenarios in a simulation study on slide 17, you were talking about, you know, omitting X by T interactions, which is the observed part of your model. I want to see what the consequence would be. And I wonder what is the bias you're assessing in this case, in your simulations. You know, is it bias due to the omission of U, or is it bias due to the omission of U plus the bias due to the omission of X by T interactions? Because you were reporting that there was small bias at the end. Could that bias, small bias, comes from the omission of X by T interaction? Then it's not necessarily the failure of your strategy. Just want to make that clear. Lastly, sensitive analysis algorithms. I think you acknowledge that a limitation of the new strategy that it requires correct model specification, right? So I was wondering, you know, how about using BART, Bayesian additive regression trees, you know, which was used in Brian's study to avoid parametric assumptions? Would that be an alternative way of carrying out this strategy? So I'll move on. I know every author will be eager to address some of the questions. Maybe we'll leave that for the end, right? Okay, 3 questions. Trang et al.'s paper, I think it's really impressive. I think they demonstrated an exemplary effort in translating obscure statistical concepts for applied research. They definitely have in their mind who they are talking to. And I think that requires a great amount of creativity and a great amount of care. And also requires that the authors have broad knowledge about the practice in applied research. I think this paper has taken pedagogy to its perfection. Unfortunately, I missed part of your talk, so my discussion will be based on your paper. First of all, a relatively minor point is I think you could add another meaningful causal effect that people could focus on in applied research. That we call it natural treatment by mediated interaction effect, which is the difference between the two NIEs, right? Which is also equal to the difference between the two MDEs. So Xu has a paper in JISSA last year showing, even based on theoretical hypothesis, the treatment-induced, the intervention-induced change in the mediator may have a larger value added to the outcome under the treated condition than under the control condition. So this is just a very quick point. A major conceptual issue I think would be very interesting for discussion is the role of SREE and its implications for defining mediation effects. The whole paper is focused on definition, right? And usually when we talk about defining causal effect, people will bring in SREE. And I think, we have to take this issue on, just briefly, it's stable unit treatment value assumption. For example, in the case we have a potential mediator M for individual I and the treatment A, this potential mediator value is assumed to be stable given the person, given the treatment condition. The same is said about the potential outcome, such as Y sub I and the treatment condition A. So my main argument is I think the definitions of the causal mediation effects are often incoherent under SREE, while coherent definitions will require an alternative conceptual framework that relaxes SREE. Now, these are big arguments. I'm not sure if I can make it clear in 2 minutes. So just briefly, we all know that the this is the treatment effect for individual I, right? It's not defined if an individual would never be treated. My example would be from the kindergarten retention study. If a child would never be retained, Y sub I0, Y sub I1, is not meaningful. So similarly, the control direct effect is not defined if in a real world individual would never display mediator value M. Say M is compliance, right? So this is not defined for compliers. Lastly, the natural direct effect is not defined if M under treatment condition 0 is not, when M0 equals M, if it's not within the support for the potential mediator under the treated condition, then this is not defined. So those are the issues. So in general, I would argue the world is stochastic and SREE is often violated. And in a stochastic framework, these potential mediators, potential outcomes for given individual under a given treatment condition are each a random variable. It should have a distribution, not a stable fixed value. And by the way, if that's the case, we can weaken the consistency assumption. And then we can talk about how treatment changes individuals' potential mediator distribution from one to the other, or change individuals' potential outcome distribution from one to the other. And these are individual specific distributions I illustrated here with the graphs. So, and here you can show clearly what is support for. I think the support idea is clear. If there's no support, the treatment effect is not defined for the individual, right? And it's important that you need the support to enable causal mediation analysis when it involves Y1 and 0. So I'll skip some of these, jump to here. The conclusion is defining causal mediation effect is difficult under SREE. I think Don Rubin would agree. If M1 and M0 are each a fixed value, will be operating in a world of principal stratification, not a world of causal mediation. So I'm happy to add more comments during the discussion.
Thank you. That was great.
I should stop here.
It is 1:57, so we're right up on time. I didn't see any questions come in on the chat. And so what I think I will do is see if each of the three speakers wants to take like 30 seconds to just respond briefly. And so maybe I'll go in order of actually, let's go in order of the comments. So I guess, Brian, that would put you first.
Sure.
Do you want to?
Yeah, that was a great discussion. Thank you. The randomization inference strategy, I really like that idea because it'll give me the distributions. There's a little bit of nuance on looking at the A does not affect, the MY path in the sense that there's some results we show where it only has to occur in one level of the treatment, which is a little bit unintuitive. And so it was the whole reason I skipped that section. But we're still trying to digest that section. Yes, 4-3 would all probably be a really good idea. Every point was great, and that was a great discussion. Thank you.
Great, thank you. Shu, anything you respond? Oh, you're muted still.
Okay, sorry. Yeah, thank you so much for the important suggestions. I think those all make a lot of sense to me, and I will definitely further try to update the paper based on the suggestions. And one of the most important point is you mentioned that why not also considering U by M and U by T by M interactions in the true outcome model to be more general. That's definitely a good suggestion, but that means that we're going to have more sensitivity parameters. In that case, we may not be able to very easily visually represent the sensitivity analysis results, but definitely that's one thing we may want to mention in the discussion section. And thank you for the suggestion on using BART to avoid parametric assumptions. And so it's so nice to hear Brian's talk and also Trang's talk. So these are actually both very helpful for further improving my paper. Thank you.
Great. And Trang, any final reply you want to give?
Yes, thank you, Quang for the discussion, and please send me your slides so that I can see all of the points. I need to
already did
one carefully in order to digest and form an opinion. I think Sutva is a very thorny kind of, in some way, a thorny topic that sometimes I just want to bury my head in the sand and not think about it. But it's definitely a topic I need to think about more. Some of the assumptions some of the points you made are related to the positivity or the overlap assumption and not specifically consistency. Well, I guess it's you can look at it in two different ways. So we are trying to write the next paper, which is about identification assumptions. And in some way, that paper deals with the positivity assumption more clearly. The Sutva, which is important for the definition of the effect, somehow we managed to write a paper and kind of skip it altogether. But yes, I really appreciate your points, and I look forward to studying every single point carefully.
Let me discuss more after this.
Thank you all.
Yes.
That's what I was just going to say. I think, you can everyone attending can see that there's a lot to discuss with mediation analysis, hard to do in an hour, but hopefully this session gave a flavor for the complications, but then also some of the opportunities for high quality and sort of careful thinking and analysis in this world. So thank you so much for this. This was my first virtual conference session ever, I think. So nicely done, and it was a pleasure to participate. I hope it was useful to all of our attendees. So, and the conversations will certainly continue in other ways. So thanks so much.